This is the last lesson of this chapter and of this course. It has a weird name, but more on that later. I want you to start focusing on these two things. First, how to get the square root of a complex number in polar form. Again, I'm not going into details, but if you have a complex number represented by its normal form, a plus bi, then you already know that in the polar form you're going to have this. So the square root of z is going to be given by what? By the square root of r, the square root of the modulus. And what is happening to the argument? You are being divided, it's being divided by 2. But you will always have two options. The first one is the one I just said, and the other one has the same modulus, but now the argument is going to be what it used to be divided by 2 plus pi. All right, so have these two as the two possible ways of representing the square root of a complex number in polar form. What if you have complex exponents? I'm not going into details into how to derive this formula, but you just need to know it. It actually makes more sense the other way around. If you have a complex number written in polar form in which the modulus is 1, basically just cosine of theta plus sine of theta times I, this is the same as just e to the power of I theta. If you eventually have a modulus, whatever it is, then you just multiply it by e to the power of I theta. And this is a very interesting situation because if you now cherry pick the value of pi, and if you pick the value of pi, no, the value of theta, and if you pick theta to be pi and substitute it over there, what are you going to have? You are going to have e to the power of I times pi equals cosine of pi plus sine of pi times I. What is cosine of pi? Cosine of pi is minus 1. What is sine of pi? It is 0. So you end up with this. You can actually put this 1 and send it to the left-hand side of the equal, and you eventually have this. And if you pay attention to this, you don't have a traditional equation, you don't have any variable there. You just have a bunch of numbers. You have the number 0, you have the number 1, you have the number e, you have the number pi, and you have the number I, which coincidentally are the 5 most important numbers in math. This is called the Euler's identity. And it's interesting to look at this, and it gives us the impression, and that's the very least, that math is not something that we invented. It's something that we discovered, because there is one equation, this one, that links the 5 fundamental numbers that we use, and by extension, it links all a math together in something that makes sense. It kind of seems that math is embedded in the structure of everything there is around us in the universe, and that's an interesting thing to think about. We're going to end with the Fundamental Theorem of Algebra, which gives us a way to solve polynomial equations with complex roots. Until this chapter, if we were talking about quadratics, that's the polynomial equation that we most focused on since the beginning of your study of math. So polynomials of degree 2. Every time you would solve the quadratic formula, and you would have you would end up with the square root of a negative number, you would stop saying that there is no solution to this equation. Actually, the actual term that you should be using was there is no real solution to this equation, because there will always be a complex solution. Let me just bring this up with an example. Let's say that I have Let me think of a quadratic. X, let me take this over here. X plus 2x, actually this. If we were to solve this, until recently, what would you have? You would have x equals plus or minus square root of minus 2. Again, no real solutions, but now you know more than this. Actually, let me take this 2 out of here and put a 4. It's more convenient for the calculations. All right? You already know that this is plus or minus. I can turn this into just 4 times minus 1, which is plus or minus square root of 4 times square root of minus 1, which is I, which is plus or minus 2i. So you indeed have a solution to this equation. It is just not real. It is imaginary, actually purely imaginary in this specific case. So what are the solutions? You have x equals minus 2i or x equals 2i. And this leads us to what the, let me just take this out of here. Why don't you just go? I'll just close it. What the Fundamental Theorem of Algebra states. It states that every polynomial of degree n, in this case it was degree 2, with real coefficients. This version focuses on situations with real coefficients, because you may have as well complex coefficients, but we are not talking about that over here. So with real coefficients, we'll have exactly n roots, real or complex, including repeated roots. If any of the roots are complex, they will always occur in conjugate pairs. I just turned it off, but I hope that you can still remember what I wrote. The roots that we had for that problem, the complex roots, were 2. And they were the complex conjugate. Remember, it was minus 2i and 2i. They are complex conjugates. This theorem says that every time there is a complex root, they will come in pairs. You can only have one. You will have 2. Okay? One complex number and its complex conjugate. And it says more. It says that if you have a polynomial of degree n, then you will have exactly n roots. They may be real, they may be complex, or you can have a mix of them. In the case of parabolas, in the case of quadratics, you will have 3 situations now. A situation in which both roots are real, okay? You usually visualize this as the parabola cutting the x-axis in 2 different places. You have the situation in which the parabola just touches the x-axis in one situation. And if you remember, the wording that you used back then in Math AS was repeated roots. Okay, why? Now you are in position to understand what the reason why repeated root was used instead of just one root. It has to do with this theorem. I'm going to pick another one. Let me just ensure that this doesn't go away. Let me take the mini board over here. It's still here. Let me think of one that works. Okay. If you have x minus 2 squared, if you try to solve this, you will have repeated roots, okay? You'll have, this is the same as, by the way, x minus 2 times x minus 2 equals 0. And you have x equals 2 or x equals 2. You have 2 solutions. They are both real, but the number, the solution to each one is the same. So that's the reason why you say repeated roots, okay? And they are real. And then you have a situation in which you will just have complex roots, and they come in pairs. Here you can see again the complex conjugate. All right? But this extends to any polynomial. Let's say, for example, that you have a polynomial of degree 4. So you may have the situation in which the 4 of the roots would be real. You can also have a situation in which you have 2 real roots and 2 complex roots. You cannot have a situation in which you have 3 real roots and 1 complex root, because if you have complex root, they will always come in pairs. Okay, I made here a little summary just for quadratics. So if the discriminant is 0, that's a situation that you know for a long time. You have 2 roots, 2 real, and none of them complex. If the discriminant is equal to 0, I just showed you an example, you have 2 repeated roots, both of them real. If the discriminant is negative, then you still have 2 roots, okay, according to the theorem, but none of them is real and 2 are complex. Okay? So the key idea, the order of the polynomial corresponds to the number of roots. Roots may be real or complex. If they are complex, they come in pairs, in which the pairs is the number, complex number, and its complex conjugate.